Himabindu from the Department of CSRT. So today in this video I would like to explain about the concept called equivalence of PDA and CFG. So PDA is nothing but push down automata and CFG is nothing but context free grammar. So here we have to discuss about the topics called the equivalence. That is nothing but we can convert the push down automata into a context free grammar and we can convert the context free grammar to a push down automata. So we'll discuss about the conversion, how to convert from one format to another format. We will discuss. So here, if you check this context-free grammar, so we can convert this PDA, push down automata, in two types of acceptance. We have one is empty stack acceptability and final stack acceptability. So we can convert this both into a two formats. So we can convert from one format to another format. If you see this diagram, so PDA is a final state. So here the string after simulation, when it is reaching the final state, so it is named as a PDA acceptability with the final state. And whenever the stimulation of the string in the PDA after consumption of all the inputs in the string, when it is reaching the stack empty, so it is named as a empty stack acceptability. So here these two types of acceptability of PDA we already discussed in the previous videos. So here we can convert this one acceptance to the another acceptance. So this is about we can convert the push down automata into a empty stack acceptability and we can convert this empty stack acceptability to a push down automata with the final state acceptability. And with this we can also convert this into a context free grammar. So here there is equivalence in the nothing but we can convert this PDA to the CFG and also we can convert CFG to PDA. So this is the thing we have to discuss. So here we can convert the push down automata into a context free grammar and context free grammar into a push down automata. So both are having the two different construction process and we will discuss that construction of the process. And here we can convert, first one is converting a CFG to a push down automata. So we already know, we know about the push down automata, how to construct a push down automata. So it requires a stack. According to the stack acceptability, we can after reading the input string, when it is reaching the empty string, empty stack is empty, so it is named as the empty stack acceptability. And whenever it is reaching the final state, that is nothing but initial top of the stack symbol, which is Z0. If it is reaching the Z0, it is nothing but it is a final state acceptability. So according to that push down automata construction acceptability, either it is a empty stack acceptability or final state acceptability, based on that we have to construct or we have to stimulate the string to the PDA. So here we are taking the acceptability of empty stack. Here we are giving the input, that is nothing but the word, the W which is represented. The word is in the form of a sequence of inputs. So here the sequence of inputs we are giving to the push down automata machine, and that push down automata, whether the string is accepted by this push down automata or rejected by the push down automata. So based on the language, so in the language we have multiple words or strings we have. We, according to the language, we have to give one input to the push down automata and we will get a result as a accept or reject. If you observe these two are without output. So we already discussed about the finite automata with output and without output. So without output is nothing but so either it is the string is accepted or rejected, and which implements this context free grammar. So based on this push down automata, we can implement the context free grammar. How to implement this context free grammar, we'll see. So here main idea is nothing but the PDA stimulates the leftmost derivation on the given W. So based on the word which is given for the PDA, with that one we can derive the leftmost derivation and we will get the we will get the production. Based on that, we have to construct a context-free grammar. So here, given W, and upon consuming it fully, it either arrives at acceptance or empty stack, or non-acceptance. So here, these are the two types. So in that two types, we will take one acceptance PDA, and based on that, we will construct a push-down. We can construct a context-free grammar from the given push-down automata. And here we have to convert the push-down automata into a main idea of this conversion is nothing but the input is given like PDA, and we have to convert it to a CFG, context-free grammar. So we already know about the context-free grammar, what are the tuples we have, and if you observe, this PDA is having the stacks, symbols and input symbols, all the transition functions, and we have to convert it to a 4-tuple notation. So what is that 4-tuple notation in the sense? Non-terminals, terminals, production rules and stack symbol. We already discussed this context-free grammar 4-tuple notation in the previous videos. And here we have to convert the given PDA into a context-free grammar. So what are the steps involved in this construction? So here, these are the steps we can perform for the conversion of context-free grammar into a PDA. And here the right hand side of first step is about the push the right hand side of the production onto the stack. So here we have given a push down we have given a 4-tuple notation. In that one is a production rule. So here we have production rules are like this. So here S is equal to AB. So here it is a one production rule. So if it is an example production rule, so in this one, right hand side of the production rule, we have to place this right hand side into a stack. So this is the step 1 we have to do for the conversion of given CFG to the PDA. So PDA which involves the stacks. So here in the context-free grammar, there is a no stack here. So we have to push the production rules into a stacks. How to push that into a stack in the sense. So here the leftmost variable A is on the top of the stack symbol. So with the leftmost symbol at the top of the stack. So this is the rule we have to follow. So here the production rule, right hand side, it is having AB. So in that one, first leftmost symbol which is on the top of the stack. So this is the top of the stack. So like this, how many production rules are there? We have to do all the production rules like this. And we have to push the right hand side of the production rule, terminals or non-terminals into a stack. So this is the first step. And second step, if the stack top is the leftmost variable, then replace it by the all its production. So here leftmost variable, if it is we have to place all the stack symbol. What are the leftmost symbols are there? We have to place all the symbols in the top of the stack. And then replace all its productions. Possible substitutions will represent a distinct path that taken by the non-deterministic PDA. So here what are the non-terminals or terminals are there? We have to place all the production right hand side of the production rules into a top of the stack symbol. So this is the second step. And third step, if the stack top has a terminal symbol. So here we already know that the grammar which is having the 4-tuple notation like V, T, P and S. So this is so V is nothing but the states. We can represent that into a finite automata. So V is nothing but non-terminals. So non-terminals are like this. See here, what are the capital letters are there? Well, those are all called as non-terminals. So the non-terminals we have to place as these, and whenever the terminal symbols are there in the production rules, we have to replace or we have to do the pop operation. So here the terminal. So here suppose the production rule, it is having the A as a terminal. This is small a represents the terminal symbol. So whenever this kind of production rule appears, so we have to pop that terminal and we have to do the pop operation. So here we have to do whenever the terminal symbol is appear, if it matches the next symbol in the input string, then pop it. So here, this is how the three steps we have to follow for the conversion of context-free grammar into a push-down automata. So simple, we have to first convert the context-free grammar, that is a four tuple notation. We have to write all the production rules, and whatever there in the production rules, right hand side of the every production rule, based on the production rule, we have to place all the non-terminal symbols into a top of the stack symbol according to the rule. First step, and this we have to follow continuously, and whenever the terminal symbols are appear, if it is matching the next symbol, we have to pop that terminal symbol. So like that, whenever it is reaching the final or empty stack, so it is a push down automata. The string which is reaching the final state or empty stack, it is a push down automata. So here, if we have some doubt like terminals. So here the V is nothing but non-terminal. So here in the push down automata, how to take the states. So here states are nothing but, here we are taking only one single state here. So that is we have to follow. State is inconsequential. So only one state is needed here. So here this is the steps to follow the conversion of given context-free grammar into a push-down automata. We will discuss more this conversion about the example. So here we have formal construction. So formal construction of push-down automata from CFG. So here what is the input here? We have to there is a CFG. The input symbol is in the form of four tuple notation like Z is equal to. So here Z is equal to V, T, P, S. So V is nothing but non-terminals, T is nothing but terminals. So terminals are nothing but input symbols. So and P is nothing but production rules, and S is nothing but start symbol. And here the given thing is CFG. CFG is nothing but four tuple notation. The grammar is. So we have to convert that to a PDA. So PDA has how many tuple notation. So here the output should be in the form of here how many tuple notation. So here Q is nothing but capital Q. We can say that it is a capital Q. Capital Q is nothing but a finite set of states, and T is nothing but sigma. And we will write as it is, T is equal to T. So that is a sigma. How many values are there? Input symbols are there. We have to convert into it terminals. And here the production rules. So production with the production rules only we can form terminals and non-terminals. So there is a combination of production rules. So here if you observe this production rule or like this. So here these are the terminals. So terminals and non-terminals. So A tends to A, B. So if it is a production rule, so in this one it is a combination word V union T. So V, here it is a terminal, and V. So here like this we have to we can form the production rules with the combination of V union T. And transition function. So for one input, for transition function is nothing but for every state we are giving one input and where it is reaching with the stack symbol. So that is a transition function. So in the transition function, we push down automata transition function also we discussed. So how many symbols are there? Triple notation is there. So in that one triple notation, the first one is about the state. So like state input symbol and top of the stack symbol, top stack. So this is the triple notation for the transition function of push down automata. And here, and Q is nothing but, So here Q is nothing but initial state, and Q is nothing but it is a final state based on the empty stack or final state acceptance. The Q is decided here, and S is nothing but start symbol, that is nothing but initial state. So here the top of initial stack symbol. So S is nothing but here top of the stack symbol. So here whatever there in the top of the stack symbol, it is equal to the S. So here this is how we have to do. Given is a 4 tuple notation, and output should be there in the 6 tuple notation. And we'll discuss what is meant by transition. So here we discussed about the transition of push down automata. So this transition of push down automata, it is having the values like A is nothing but terminal, so V is nothing but non-terminal, so it is belongs to V, and add the following transition in the PDA. So if the top of the stack symbol is A, so here we discussed about the initial input sim. So this one is about the input sim, present state, and this is the input symbol, and this is the top of the stack symbol. So whenever the top of the stack symbol A or term V, one of the V symbols are appeared, how to elaborate this one? So how to convert this to a production rule? So production rule transition function. So it is having the present Q is the present state here, and this is also a next state, and with alpha. So this alpha is nothing but in the production rule. So suppose this is the S tends to AB is there. So in that one, so S tends to AB, this is the production rule. In this one, according to this equation, A is S here, and alpha tends to alpha is nothing but AB. So what we have to do in the first step-by-step process, we have to push that symbols into a stack. So how to push this one? So right hand side of the production rule, that we can convert that into a stack symbol. So here we have to represent. So here this is nothing but the belongs to A tends to alpha. So A tends to alpha, which is nothing but it is a production. So we have to convert. How to convert? So here the next state and alpha. So how many are there? So suppose here the production rule, which is having one more production rule in the same thing, how to represent? So A. So suppose S tends to A is there. So here we have to add Q comma. Here for this production rule, I will write AB, and next Q comma A. So here how many production rules are there for the right hand side of one non-terminal symbol? We have to add like this. So it is a process for the conversion or transition function of the push down automaton. And here after before conversion A, so here the A is there, and after alpha we are replacing in the production top of the stack symbol. So we have to write this alpha. So here already we have written instead of this A, we are writing AB, and instead of S here we are writing AB here. So this is before and after. So based on the production rules, we have to follow the moving of this symbols into a stack. And for all A tends to terminal, so here A tends to terminal there. So in the production rule, so suppose here transition of Q, present state, and the terminal. So here input symbol. So this is the input symbol, violet A is the input symbol, and here the top of the stack symbol. So here suppose the top of the stack symbol is A here, and here for this production we have to replace A with the AB. So here whenever this kind of A terminal is appeared, so it is, if it is matching the input symbol, we have to pop the A. So that what is the pop operation? Q comma epsilon. So here this is the situation whenever the terminal appears. So whenever it is a non-terminal, we have to push the symbols into a stack, and whenever the terminal appears and it is matching with the input symbols, we have to pop the stack symbol. top of the stack symbol. So before A is there, and here after this one the arrow marks, that is nothing but A is popped, so arrow top of the stack symbol is down to the A. So this is how we have to convert the push down automata. It is a formal construction. So let's see the with this construction with the example. So here input is about context free grammar, and we have to convert it to a transition functions of push down automata. So first one, so 4 tuple notation. So in that one, S, V, this is nothing but V, and T and P and S. And we need production rules also. So what are the production rules? So here are the production rules. So we have 2 production rules, and so here, and push down automata. So while converting the given grammar into a push down automata, first thing, so only one state is needed here. So that is written as a Q, and 0 1 is the sigma. So the sigma is nothing but terminals 0 1, and V union T. So V union T, it is a combination stack symbol. So whatever there, we have to push the symbols, like these are the if it is a stack, so in that stack symbols, so these are all called as stack symbols. So whatever there in the production rules, we have to push that into a stack. So on transition functions, we have to write and Q and S. S is the top of the stack symbol. So top of the stack symbol is, so initial first state, first production rule starts with this S only. So we have to push the top of the stack symbol. So top of the stack symbol is here. Transition function, it is having the 3 tuple notation. The first one is about current state. So current state with the input symbol epsilon, and when we are giving this top of the stack symbol S. So what are the top of the stack symbol production rules? So production rules, so first what it says, S tends to AS. So right hand side of the production rule, it is AS is there. What we have to do instead of S, so top of the stack symbol. So this is the top of the stack symbol. We have to push that into A and S. So here like this, so for the first production, and epsilon also. Oh, epsilon also is there, and we have to write this epsilon. So here, and next A. So how many production rules are there? Right hand side we have to push. And next transition of a next production rule. So how many V symbols are there? So first S is there, and next A is there. So A is nothing but top of the stack symbol is A. What top of the stack symbol is A. We have to push that A with the replace it with the what are the production rules of the right hand side. So 0 1 and right hand side. So and A1 and 0 like that. So here we will reverse this one. 0 A1 and 0. So here instead of A, we are replacing all this production. So what are the productions? So here these are the values for this transition function. So and next, and whenever we already discussed the third step, whenever the terminal which is matching with the terminal symbol, terminal appears. So here the terminal appears. So in this also we have to push like this. So here write A1 like this we have to push. And here top of the tag symbol is 0, and whenever the input symbol is 0, we have to pop the A. So this is happened here. So here empty is empty. So epsilon is there. So and for the transition of 1 comma 1, so whenever it is matching with the 1 input symbol, we have to pop. So here like, so suppose here the top of the stack symbol is 1. So here we have to pop the 1. Like this, we have to form a transition function for the productions. And we can convert these production rules into a diagrammatic representation. You'll see. So S tends to, so whenever we are giving the epsilon as a symbol, so it is in the same state S, and top of the stack symbol is S, and we are pushing S. So whenever epsilon is there, we have to push top of the stack symbol. same, and nothing will be happen. And whenever we are giving epsilon as an input symbol, epsilon as an input symbol, as the top of the stack symbol is S, and we have to write this production rule also, AS. So this is about this one, and epsilon. And next, so top of the stack symbol is A, and this we have to do. So every step, so for the single state, so here if you observe this PDA which is after converting a given CFG into a PDA, we have only one state. So for the one state we have to repeat the loop. So how many transition functions are there? So every transition function which is in the self state only. So here this is about the conversion, and remaining all, if top of the stack symbol is A and we have three production rules we have to write, and top of the stack terminal is there, and top of the stack symbol is 0, and we have to pop, and top of the stack symbol is 1, we have to pop. So this is about the conversion of given CFG into a push down automata. And how will this new PDA work? So here after converting a given CFG into a push down automata, we'll check with one string, and we will pop the we will push the elements into a stack, and whenever it is reaching the empty stack, if it is accepted by the push down empty stack acceptability, we will stimulate one string for this newly constructed push down automata. So here is the string we have taken 0011. So two zeros are followed by 2 ones. So here, so we have written already, we have discussed about this conversion of transition function. So here this is the diagram, and we have to take this 0011 string, and first step what we have to do, we have to derive a derivation for the leftmost derivation for the production rule. So whether the string is accepted by this given grammar or not will change. So here production rules which are started with S. So I'll take AS. So first is AS. So if you replace this substitution, so we will get the 0011. So that this string we will stimulate the string with this newly constructed push down automata. So first step is A. We have to push that A into a stack. So S we have to replace it with the AS. And here the top of the stack symbol is A here, and for the A, and this is the input string. So what we have to replace? So the second step is, instead of A we are replacing 0A1. So here instead of A we are replacing it with the 01. And here after replacing, whenever the 0 appears, so input string it is having, and again we have to pop. So in this production rule we have to apply. So input string it is first 0, so 0 appears, so we have to pop this 0, and here this next the top of the stack symbol is A here, and A we have to replace A with the production rule 01. So here what we have next step is A replace it with 01, and after including this A with the 01, the top of the stack symbol is 0 here. Again we have to follow this transition function, and we have to pop the 0, and we have remaining ones are there, and 1 for the one production rule we have to follow the one production rule, we have to follow this transition. So whenever the terminal symbol, so already we consumed 0, 0, and next we have to consume 1, 1. So 1 appears, so input symbol is 1 here, and the top of the stack symbol is 1. What step we have to do? We have to pop the top of the stack symbol 1. And next, so again the 1 input symbol and top of the stack symbol is 1. We have to pop that again 1. And S is there. So we have one more production. So that is S tends to epsilon. So whenever it is S appear, we have to replace it with epsilon, and the stack is empty. And here it is the empty stack here. So the string is accepted by the empty stack acceptability. So this is how we are stimulating the input string and with the newly constructed PDA. So here this is the equation. So A tends to, so what is the new leftmost derivation we derived from the production rule? So that is here followed here in the push down automata also. So this is how we are converting a push down, we are converting a context free grammar into a push down automata. And one more next one is we have to convert the push down automata into a context free grammar. Till now we have seen CFG to PDA. So input is like production rules, we have to convert into a transition functions. So here in converting of push down automata into a push down automata to context free grammar, we have to reverse the process. So transition functions to production rules we have to convert. So what is the step by step process? We'll see. So here the main idea is reverse engineering the productions from transitions. So productions we have to derive a production rule from the given transition function. So here the production rules we have to how to derive in the sense. So transition functions, so it is having the three tuple notation. The first one is the state, so state, current state, or next input symbol and top of the stack symbol. How to convert that into a production rule? So here the next state here and y1, y2, y2, and here what are the terminals? So what are the terminals are consumed? So top of the stack symbol z is popped and replaced with a sequence of k variables. So we will replace it with the sequence of k variables. So how many variables are there? We have to convert that into a production rule. So how to convert? So create the grace p is a variable, grammar variable called QZP. So Z is nothing but, so top of the stack symbols. So that is varies from one transition to another transition. So how to derive this Z in the sense here? Z is nothing but A is nothing but it is the terminal symbols which is followed by next state and next state sequence here y1, y2, y2. So this is how we have to follow. And to avoid the confusion here, bracket matching. So bracket matching in the sense, suppose the text it is having this kind of bracket. So we have to match every starting and ending braces. So otherwise the string which is in the in between this then, so suppose then is the string which is in between the bracket. Suppose we are not closing these braces, so it comes under this next braces. So then it may causes confusion. To search that kind of words in the form of mathematical model, we have to follow this push down automata. So for this kind of grammar, how to construct a push down automata. So here. So whenever, this is how we are constructing a push down automata. So we have to avoid confusion. So starting brace is B and ending brace is E. So E and B. So these are the two input symbols we are giving, and Q is the only state we are taking, and that is named as a Q naught, and Z naught is the initial top of the stack symbol and transition function. So what are the transition functions? Suppose here in the top of the stack symbol, whenever the starting brace or starting the B appears, we have to pop for the E. So whenever the input string it is having the E, we have to pop the top of the stack symbol is B. So here this is the thing we have to convert, we have to construct a push down automata. So here what is the step? So whenever B appears, we have to push that into a stack. So top of the stack symbol is B. So input symbol is B and top of the stack symbol is Z naught. So B appears, we have to push that into a Z1. And next, whenever B from the state, top of the stack symbol is Z1. So how many times Z1 appears, we have to push that into a Z1, into a stack. So B appears, we have to push. And whenever E appears, we have to pop. That is the simple logic. And here E appears and top of the stack symbol is Z1, we have to pop. So this is the done. And again epsilon is there. So until this top of the stack symbol is Z0 and we have to pop this one. And whenever E appears. So here and whenever the empty stack. So we consume the two inputs. So here B appears. So this is B and E. So it is matched. So nothing is there in the stack or only Z0 left. So for this kind of situation, after these two strings, so epsilon is there. So epsilon for the input string epsilon. So top of the stack symbol is Z0. So we have to pop that one also. So this is the step-by-step process. We have to construct a push-down automata for the braces matching. And now we convert this push-down automata into a context-free grammar. How to convert? So here we are taking the input symbols. So based on the transition functions. So S is the start state here. So S we are taking. What is that S? So what is the top of the stack? Top of the stack. So Z0, so top of the stack symbol is only Z0 left and Q0. So here this is the S. And next for this transition function, we have to follow. So B appears for the terminal B and how many are there into this push down in the top of the stack symbol. So for every individual symbol, we have to follow. So B terminal and Z1 there and Z0 there. So separately we have to write. And for the B terminal and the same thing, two Z1s are there. For every Z1 we are doing like this. And one more, this is about the Z1 and we have to follow. So for the Z1 input symbol E, so whenever E appears, so we have to follow. And epsilon we have to follow. So this is the step by step we are converting a transition functions to a push down production rules. So we will name this Q0, Z0, Q1. So and instead of writing whole thing, we will replace with the terminals what V symbols. So V symbols are nothing but non-terminals. So here non-terminals A. So A is nothing but this one and B is nothing but Z1. In between only one state we are taking, that is a Q0. So B and A and B. So with that it extends to A and A tends to terminal and which is followed by BA and next BA, BB. And after simplifying, instead of writing all the production rules, we will write directly S tends to A tends to A. S tends to A tends to A. So we will replace it with the direct production rule BBS. And also we have A tends to epsilon, that is we are writing. So A is nothing but S. So S we will write directly. And B. So B is nothing but it is having the two production rule. We will write this simply in the one production rule. So this is how we are converting that given push down automata into a production rule. So one is nothing but we have to input is transition function, we have to convert that to a production rule. So this is about the conversion of push down automata to a context free grammar. And here the two ways of to build a context free grammar. So we already discussed. So building a push down automata, we can construct directly from CFG to PDA, and this is the indirect way. We can also derive a direct CFG directly. So this is the directly and indirect. If you want, if they are giving the input in one form, we have to convert that in another form. That is the indirect way. And here for the same thing, derive a CFG. So we can construct a PDA from CFG. So that is indirect, and design a PDA directly. So designing a PDF directly, we can say that this is a designing a PDA directly. And here this is a designing a PDA from the previous conversion from the context free grammar to a push down automata. So this is about the conversion, the equivalency of push down automata to context free grammar. So these are the references. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.